Okay, thank you very much for the kind introduction. So yeah, today I will present my work, or our work, efficient explainable face verification based on similarity, score, and backpropagation. It's a work I did together with my master's student Lu, my former colleague Philip Terrace, now at Paderborn University, and my supervisor Nazar Dahmer. I presented it in the beginning of this year at the WACV conference, so the Winter Conference on Application of Computer Vision. If we have some time, I will also go into another paper, which will be actually presented next week at FG, or to be more precise, at the International Workshop on Responsible Face Image Processing, and it builds up on the idea I present first. So let's come to the motivation. So I think every one of you may use or have been used face recognition systems. They're becoming more and more important or ubiquitous in our everyday lives. We use them at the airports, we use them to unlock our phone. And the problem is, or why we need to better understand the systems, is because they are based on deep learning, which means, of course, you all know, I think, that we don't really understand what's going on there. They are highly complex, they have millions of parameters, and we want to know better what's going on. Because first of all, we are working on security-related areas. We use them to get access to mobile phones or to flights. We also process private data. The face is defined as private data by GDPR, and we want to know if a system processes our private data, what's going on. We have also the big problem of bias, where we say, okay, specific ethnicities, specific genders are discriminated by systems, and we want to better understand why this is the case and want to find ways how we can mitigate this bias. Although what makes explainable face recognition a bit different from explainable AI in different fields is that it's different from just explaining classifications. As you may know, GradCam, ScoreCam, all these class activation maps that are frequently used. And in the biometric systems, we usually don't have a classification system, but we have some embedding process. So we don't have the classification systems because the training IDs are not the same, or training classes are not the same as the testing classes, because usually we all are not part of the training data, hopefully. So we need a way to find how we can use AI to use them besides classification. And what is usually done is that we have some embedding network. So we have this should be a convolutional or representation of a convolutional network, which maps your face interface to mathematical representation in a feature space where your face is mapped to mathematical representation. And then during verification, so assume this is an image stored in your mobile phone, then you would get another vector and they are then compared. And if the vectors are similar enough, this face embeddings, then it would be considered a match. If they are not similar enough, they are not a match. And the threshold to be chosen, that is chosen to say if it's a match or not, is often system dependent and depend on the use case. If you have a high security scenario, you want to acquire a higher similarity than if you use it for your mobile phone. So far to the introduction to, although I get everyone into the biometrics terminology. So let's talk a bit about related work. So the idea is now we want to explain or understand why two faces match or do not match. And there have been several works proposed on how we can get some visualization that highlights which are the face features that are important for the model's decision. One work which the idea is to say we can add a learnable module on top on our face, or on our embedding network, to then learn what are the important parts. What they basically do is they, instead of getting a feature representation, they change the flattened and fully densed or fully connected layer to a 1x1 convolutional and get there like a patch representation of the face. And then they can, for each patch, they can calculate the similarity on this patch-wise representation of the face. And in an additional step, they also learn an attention mechanism, attention module to overweight the difference or the similarity of the patches to get an even better representation. So what they do, to put it shortly, they try to split the image in different patches and then see which areas of which patches are more similar to each other. Has a limitation, as we later see, that like all the explanation is patch-based, so you don't get like a more free structure. A second approach is to do systematic occlusion, which is rather simple. The idea is, okay, we have our face recognition model and we just manipulate the input. We systematically occlude it. I have the studio algorithm here, so we just go over the image. You mask certain areas and see how the output changes. And if this image or the comparison score between image gets more similar, increases, then obviously you have occluded, masked an area which contained information that makes the image more dissimilar, and the other way around. And there are three different approaches, but yeah, more or less the same. It just depends on how they compare, how the impact of the image are. So I present this works because these are the main works we compare with, and they are kind of the state of the art. So let's come to our approach. We decided, okay, we want something training-free, and we want something that is fast. Because like a lot of this perturbation-based approaches take a lot of time because you have to do hundreds of forward passes to then estimate or get how the impact is. So we decided to do gradient-based approach, and I will go into detail soon. And we also decided, okay, we need to find a better way on how we can evaluate how good our explanations are. The most related work, or the related work I showed you, never evaluated in a quantitative way. Most of the time, they just show their maps and then start to argue, okay, you can see the eyes are highlighted, that's mean that the eyes are similar, but it's hard to get a quantitative analysis or evaluation which approach performs better. So let's come to our approach. So we have the same setup you have seen already. So we have two facial recognition models, which takes an input image and maps them to some embedding layer, or some embedding, which is just activation in this layer. And at the end, we also have the similarity calculation, which in this case is just cosine similarity. In this case, it's also simplified because the embeddings are normalized. And yeah, so we have this setup. And what we now investigated, or what motivates our ideas, as you can see here, if we calculate the cosine similarity on the normalized embeddings, we can see that the score actually increases if the features in a certain dimension goes in the same direction, otherwise the score decreases. But what's now new, what we added here is we were thinking, okay, we're always talking about similar and dissimilar regions. But what we actually want to know is if they are positive or negative for the decision. Because it might be the case that areas are similar, but they are not similar enough to reach the threshold. So just having a similarity, or just saying that things are similar, does not mean that they are actually contributing to the decision. So what we introduced was to make a split between which features are positive in the sense that they at least participate their share. So we said every feature should, like as you can see here by the definition, we divide the decision threshold by the number of dimensions we have. So each dimension should at least contribute the times his share. I hope that you could get clear what I meant. And so we decided, okay, we split each dimension either belonging to the positive or negative argument, depending if it does his share to reach the decision threshold. And what we then did, okay, we calculate the gradients based with regard to the input image. So we can get, there are a lot of works who are doing something similar with like the gradients tells us how many or how much a pixel have to be changed that it influences the feature the most. So we just do backpropagation, but we split or do backpropagation either for the positive arguments or for the negative arguments. And in the final step, we take the mean over the colligens, and then do a combined map where we subtract the negative map from the positive map to get a final representation, which we call the combined map. So let's come to some experiments and experiment setup. So we evaluated on 4 state-of-the-art face recognition model. We have ArcFace, which is kind of all-time highlight. Everyone is using it. It's quite old, but it's still very competitive. There are 2 extensions, Elastic Face Arc, Elastic Face Cos, and also another recent one, Curricular Face. I also put here performance in LFW. It's equal error rate. It's not normally the measure to or quality measure or performance measure on LFW, but you see soon why I put equal error rate here. For the comparison with state of the art, we choose XCOS and XFace. It's the related work I just showed to you, and we also included a random baseline, which randomly generates explanation maps. For the evaluation data set, we created patch LFW, where the idea is based on LFW, which is like the standard benchmark for face recognition, and it's kind of soft. The performance is 99.82 or something, so it's kind of solved because there are also mislabeled images in the data set. And what we want to look here is, as I kind of started to tell you already, is that we are mainly interested in the errors or understanding the errors of the system. Because it's interesting for us, okay, why did someone get access to a system and not why did I didn't get access? Like it's most often it's more costly to have an error than having correct. And it's different, for example, to medicine, where you often want to understand why this decision is. In our case, we are most interested in understanding why does our system fail. So what we did for patch LSW was we choose a matching pair, a genuine pair, and then randomly added patches from a random image on the image of one of the pair, and to make the decision flip. So now we have, instead of a matching pair, which is normally a matching pair, we now have a non-matching pair by artificially manipulating the image. And the same we do for the non-matching pair, so it's 2 different persons, and in this case we added the patches from the original image, so the same image, to make the non-matching pair now map. And what we can now do in our evaluation protocol is to say that we manipulate and replace pixels in the patches based on the explanation map. Though there is this insertion and deletion curves, which is usually used for evaluating explainability methods, where the idea is if you have some image, some class image of cow or something like this, and you get an explanation by the explanation method, you then start in insertion case, or let's start with deletion, you just delete the most important pixels in this map, and then you investigate how this changes the performance of your classifier. And if your model is good in identifying the important pixels, of course the quality or the performance should drop fast. So fast fall in performance indicates that the model officially or obviously detected the most important pixels. And in the insertion it's the same, just the way around. So you have to start with a blank image and just put in the most important pixels, and then the performance should increase faster than if you do random or the least important pixels. And inspired by this approach, we propose to do something similar, but instead of removing the pixels or adding it, we just manipulate the images in the patches. So we kind of evaluate how good is the model in detecting the added patches, because this obviously is the reason why the decision is wrong. And then we iteratively go over it and also calculate or compare the false match rate and the false non-match rate. And as you can, for example, here, we have the patch LFW, we have blend our explanation map, and you can see here slightly that there's 10% of the pixels of the highest pixels being removed or adjusted, which means we just put in the original pixels there. You can see how the patches get slightly removed. And we can use this to evaluate how good our model is in pointing at the patches. So let's see some qualitative results and also compare with state of the art. So we have here false non-match, false match. We have our map, and we have state of the art. So as you can see, the way how things are visualized is quite different. So we have here like a patch space as I introduced. So you can see it's not as fine as X-phase or our approach. In the way it's visualized, our base is the most fine, granular representation, and the X-phase has more like, which is a focus on different blobs of importance. But yeah, what you can also try to see is how the things line up with the patches, but it's hard to visually see this. I also have some more where we then do again like the replacement, and I think it's more interesting to actually see the quantitative results. So here we have like the insertion and deletion maps. We have on the y-axis, x-axis, the replacement percentage, and here we have the false match rate and the false non-match rate. And in blue we have our approach, in red, orange, and yellow the X-phase, and for this model, green ones are the cross-phase models. And what you can see is X-phase is better than our approach, but we are better than red, and also better than the X-cross approach on all the 4 different isolation models, and on false match rate and false non-match rate. And you say, okay, it's not better, but why should we do it? What is the reason to have an approach that is not better than other approaches? And what we argue is we are far more faster, more efficient than state of the art. We did some experiments running 100 random pairs and tested how long it takes. And yeah, we are faster than X-phase approach, slower than X-cos, but just the drain and X-cos, as you saw here, this performance worse. Now you may ask, okay, why is it important to be fast in explaining your face recognition system? You could argue that, okay, if you're standing in front of a border guard and you don't want to wait 1 minute, but I think what's more interesting is what I want to come next to is how can we use, or what is actually the benefit of having an explanation, and how can we use it, for example, during training or in other cases where you need to have a lot of explanations or want to generate a lot of explanations to maybe support the model in its behavior. So with this, I quickly conclude what I showed you. So I introduced to you state of the art a bit. I gave you my motivation, and I showed you the approach we developed to do efficient explainable face verification. Where does it go? Okay. And also the idea how we came up with an idea how we can evaluate explainability. So yeah, so I just made a small slides. The work will be presented next week, just to give you an idea of what we thought we could do with using the explanations. It's accepted, not yet published, and I just have some figures and tables, so it's just to give you an idea. So the paper is called Recognition Performance Variation Across Demographic Groups through the eyes of Explainable Face Recognition. And what the idea was, okay, we have an approach that can, to some degree, explain you why two faces match or don't match. Can we see, or better try to understand, the performance variation or bias? Performance variation is like an official ISO term now, as far as I know. And the idea was, okay, can we understand bias better? And the first thing we need to do, or what we thought we would do, is, okay, let's get more biased models. If you want to observe something, you want to analyze something, every face recognition model is biased, but we want to see, okay, can we get a more biased model? So, and of course, the easiest way is to say, okay, let's train the model and just neglect some data. So we train one comparison model, which is train all the data, And then we trained 4 different models to train on an ethnicity balanced data set, but we neglected either one of, or always one of the ethnicities. So we trained a model without African images, without Asian images, white images, and Indian images. And as the results show here, you can see that the performance, especially on the group that is not part of the training data, of course, drops. So we use 12% of accuracy if we use a model trained without Africans on Africans. So the models we have right now with training on separate data is more biased than even normal data, the normal model trained on all the data, which is also quite biased. But after training with different models, we decided to test especially the models either on the full model, but also on the biased model. So we evaluated the explanations split by if it's a true match, a false match, true non-match, or a false non-match, so the correct cases as well as error cases. And we evaluated, for example, the African data set using the less biased model as well as a more biased model. We generate the mean explanation maps for all false match, true non-matches, and false non-matches. And then we did a spatial analysis. What we want to see there is, okay, how does the explanation change if the model is more biased? Does the model, if it's more biased, look on different parts of the images? How does it shift? And what we do to get a visualization that we can easily compare, we just summarize over the axis. So we just summarize over all the rows and all the columns to get like this measurement over the mean maps, where you can see the values or like explanations, for example, here are higher in the blue case than in the orange case. So we can visually see how different they are, because it's hard to see the difference between these images. So came up with a way to visualize the difference in the map in a more easy way. And yeah, here are some more results. We did it once with the spatial intensity map. So in this case, we just normalized over all the images or all the maps in the data set to get them kind of aligned. But you can see that the comparison model, which is less biased, have higher activations or higher explanation power intensity than in comparison to the more biased model in most of the cases. What we also did was to look, okay, if we normalize the intensity, how is the shift in positions, just a spatial change. And you can see that also if we normalize in terms of intensity, you can see here, for example, that although it shifts a bit, so in this case, the focus is shifted a bit, it's less bias from the eye area, which would be here, because the image is aligned, to, for example, the nose area. So we can somehow relate this. This work just like the first exploration on how this might be used. There's still a lot of work needs to be done in this area, but I think it was the first approach. It is the first approach to how we can apply explainability and the idea of explaining bias. And I'm a bit faster than expected. I'm sorry if I got this too fast, but yes. I hope you enjoyed the quick introduction into this work and the small additions, how we try to get explanation, how to apply it and find use cases for it, besides showing it to users, end users. And yeah, if you have any questions, now is the time. And yes, thank you very much for your attention.